In your daily life and different branches of industries, there are many cases in which it's required to know the temperature of the environment, inside a reactor, winding of an electrical machine, and so on. Man has invented different technologies to do this. But why different technologies? This is because of different applications which make one technique better than the others for each specific case, and there's no unique way recommended for all applications. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. Most likely you've heard about RTDs, thermocouples, thermistors, semiconductor type elements, and so on, which will be addressed here. Before I get into details on this subject, let's see what a temperature sensor or temperature transducer is, and what does a temperature transmitter mean. Generally, a sensor or transducer is a physical device which is capable of transforming one type of process variable to my favorite signal type. To elaborate on this generalized sentence, let me give you an example. Temperature, pressure, flow, etc. are some process variables, and actually, they are physical characteristics of our real world. With modern technology, and because of tremendous advances in electrical engineering in the past century, we like to transform every measurable process value into an electrical signal, and a temperature sensor is a device which will transform the temperature into an electrical signal, no matter how tiny the amount of this signal might be. So far, I took a big first step, which was the transformation of temperature into electrical signal. Based on different sensor technologies, this signal may have different ranges, and for industrial applications, I need to have my signals limited to some universally accepted electrical signal ranges. Today, some of these globally accepted electrical signal ranges are 4 to 20 milliamps, 1 to 5 volts, 0 to 10 volts, etc. A temperature transmitter is a device which transforms the tiny output of a temperature transducer to one of these standard signal ranges. Now, let's get back to different temperature transducer technologies. RTD, or resistance temperature detector, is a device, the resistance of which varies with the temperature. Since it is a passive device, an external electrical current should be applied to it, and then the voltage drop across it can be measured. This voltage is a good indication of the temperature. When referring to such a device as passive, it means that the device needs an external current or voltage source. To state the obvious, a big amount of external current can cause power dissipation in the resistor of RTD and lead to excess heat. So, to avoid this type of error, the current should be kept at a minimum level. This wiring diagram shows the simplest application of an RTD, called two-wire configuration. More accurate reading calls for three-wire or four-wire configurations. In reality, the distance between the temperature sensing point and measuring system calls for wiring, and since the real wiring has its own resistance, some measurement error sneaks in hereby. Three-wire and four-wire solutions are developed to remove this error. One of the most common RTDs is PT100, which consists of a thin film of platinum on a plastic film and shows a resistance of 100 ohms at 32 degrees Fahrenheit. Its resistance varies with temperature and it can typically measure temperatures from -330 to 1,560 degrees Fahrenheit. The relationship between resistance and temperature of PT100 is relatively linear. PT100 is just an example of platinum RTDs, and in the industry you may find different RTD types suitable for various applications. For example, copper, nickel iron, etc. Thermistors are temperature-dependent resistors and are widely used in industrial purposes, such as overcurrent protection, self-regulating heating elements, inrush current limiters, and so on. Thermistors can be NTC or PTC. In NTC, or negative temperature coefficient thermistors, resistance decreases as temperature rises. NTCs are commonly used as inrush current limiters. And with PTC, or positive temperature coefficient thermistors, resistance increases as temperature increases. PTC thermistors are commonly used as overcurrent protection and in resettable fuses. A thermocouple, or simply TC, is comprised of a couple of specific dissimilar wires joined together, forming the sensing point or junction. Based on physical characteristics called thermoelectric effect, when this junction is placed at different temperatures, different millivolt signals are generated which can be interpreted as an indication of the temperature. In comparison with RTDs, thermocouples are self-powered and require no external excitation current source. Thermocouples are commonly used for furnaces, gas turbine combustion chambers, high-temperature exhaust ducts, etc. The main restriction of thermocouples is the accuracy, which doesn't make it the best solution for precise applications. Also, thermocouples need a reference measurement point called cold junction. The thermocouple junction is often exposed to extreme environments, while the cold junction is often mounted near the instrument location. Based on range of temperature measurement, sensitivity, and some other factors in each application, different types of thermocouples are available. For example, E, J, K, M, N, T, and so on. For instance, Type J is made up of iron constantan combination, with a range of -40 degrees Fahrenheit to positive 1,380 degrees Fahrenheit, and a sensitivity of about 27 microvolts per degree Fahrenheit. While Type K, chromal aluminal, is one of the most common general-purpose thermocouples with a sensitivity of approximately 22.8 microvolts per degree Fahrenheit. Type K is inexpensive, and a wide variety of probes are available in its -330 degree Fahrenheit to positive 2,460 degree Fahrenheit operating range. Since the functionality of thermocouples is based on thermoelectric effect in different types of conductors, when the location of a thermocouple is far from the measuring instrument, for example the electronic transmitter, the proper type of conductors should be used for extension purpose. Otherwise, the tiny signal generated by the thermocouple will be added with some error at the point where the thermocouple wires are connected to the extension wire. Semiconductor temperature sensor is based on the fact that the junction voltage across a PN combination of semiconductors, like a diode junction or base emitter junction of regular transmitters, is a function of temperature. This technology is vastly used in electronic devices and IC technologies. Linear characteristic, small size, and low cost are advantages of this technology. But it should be noted that the limited range of around -40 degrees Fahrenheit to 248 degrees Fahrenheit makes it suitable for specific applications. To wrap up this video, the comparison between different types of temperature sensor technologies is a multifaceted task. For example, If accuracy is considered as the key performance indicator, usually RTDs are better than thermocouples, approximately 10 times more accurate. From the sensitivity point of view, while both RTDs and thermocouples respond quickly to temperature changes at similar costs, thermocouples are often faster. If I have to measure electronic PCB and/or IC temperature, silicon-based types are the best choices. Also, alongside the technical bonus-malus comparison, sometimes cost is the key factor in selecting the proper device. As they say, money talks. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.